Today I'm going to talk about nested decomposition. There will be a lot of content, so the proof of convergence I'll probably cover it next week. At first, when you see some of the slides on this presentation, you will think to yourself, he's got to be kidding. But after we process it, hopefully it won't look too bad. Okay, so again, following Matthew's recommendations, I've put a preview of the algorithm and the idea without any math, and then we can see it in mathematical form. Bonjour. So we've entered the realm of multi-stage optimization, so we're looking at multiple time periods. Here I'm representing uncertainty in terms of a scenario tree. It's not the only way you can represent uncertainty, but it's very helpful to think of a model of uncertainty that evolves like a tree in order to understand the algorithm. So for the rest of the lecture, just think scenario tree. It won't hurt any of the generality. So here you're looking at a three-stage problem. And the way I'm gonna, the circles represent scenarios of what could happen. And the way I'm gonna number the scenarios is top to bottom, and every time I move to a new time stage, I start from 1. So for period 1, this is scenario 1. For period 2, this is scenario 1, scenario 2. For period 3, this is scenario 1, scenario 2, scenario 3, and 4. And the goal of solving this whole problem is we're solving it presumably at or before time 1. So we want to know what we should do at time period 1. So there's a symmetry in this drawing that could give you a hint of how you could approach this problem. By symmetry, I mean this looks like a two-stage stochastic program. This looks like a two-stage stochastic program. And once you've solved these two guys, this, from the point of view of sitting in the root, the rest looks like a two-stage stochastic program, provided that the solutions of the value functions at these points are this piecewise linear structure that we've seen already. So that's really the heart of the algorithm. Is we know how to solve parts of this tree, from period end of horizon -1 to end of horizon. We know how to tackle that using two-stage stochastic programming. You can use L-shaped methods, multi-cut L-shaped methods. They're both valid approaches. They attempt to do the same thing, to build an approximation of the value function. But the heart of the idea that we're going to look into today is that once you've solved these parts of the tree, then sitting here and looking down the line, you can think of this as one node, this as a single other node, and all of a sudden the whole thing looks like a two-stage stochastic program again. Is this evident? The graphical, like the symmetry here. Now, there's a little but over there. What is it that you want to make sure is true before you jump to that conclusion? What was the one? So, what was the trick that we used in the L-shaped method? The geometrical trick we used. We use this theta, right? So, can you always do that?
In the first iteration?
Come again?
That's in the first iteration.
Right, in the first iteration you completely ignore, but there was a structure in the costs. Piecewise linear, and therefore, yeah, well, a piecewise linear convex, exactly. So this trick of introducing an auxiliary variable and then lower bounding it by cuts, which are affine functions of x, is going to work well, provided the future cost of what you do today, so the value function, the v of x, is a piecewise linear function of x. So for this algorithm that I'm pitching to you, what is a requirement to keep this structure? What would we like to have in terms of future costs sitting at node 1? So we have at node 1, time period 1, we have a current period cost, the C transpose x for that period. But then we also have an expected future cost of what we do now. What would that value function ideally be like? Piecewise linear. If for some reason that value function turns out to be something nonlinear or concave or whatever, the whole trick I've done with adding a theta and then optimality cuts, it breaks down. Now, can you think of why it is piecewise linear?
Sum with positive coefficient of convex function.
Come again?
It is a sum with positive coefficients
of two piecewise linear functions, exactly. So if I can draw this graphically, when we're sitting at time period 1, this is not rigorous, what I'm going to say, but it's a way that I think of it that, for me, it's very helpful. When I'm sitting here, I'm trying to minimize some cost C transpose x plus V of x. And this V of x is expectation of the cost here plus the cost here. The cost here is C in time period 2 transpose x of 2 plus the cost to go from here down the line, so V3 of x2. And this is for scenario 1. And then we have for a decision for scenario 1 and for scenario 2. So, but these guys, I haven't written it explicitly here, but there's a bunch of constraints here also that link it to the previous time period, and those constraints create piecewise linear dependence on this x. So this function here is a piecewise linear function of this x that comes from the first period. This function here is a piecewise linear function of x. So when you sum up these two piecewise linear functions of x, the v of x is piecewise linear. The notation here might be a bit confusing because I haven't written also the linear constraints of the second stage problem. But this is the idea. You have piecewise linear function of x here, the same here. When you add them up, that doesn't get lost geometrically. That's the idea. Okay, so we know what the building block is. It's the problem we've been solving in two-stage stochastic programming in the L-shaped method. That's going to be what we're going to be solving over and over with different input. So I'm going to call that the NLDS, which stands for Nested L-Shaped Decomposition Subproblem. And I'm going to index it by a time period and a scenario. So how many of these did I have in the previous tree, since I'm indexing it by time period and scenario. I have 7 of these, and when I solve them, I can generate 2 possible things. An X for that NLDS, which I can send forward as a trial decision in the same way that we did it in the L-shaped method. So if you remember, the first thing we did in the L-shaped method is to solve period t equals 1, throw the trial decision to the next time period. So when I solve an NLDS sitting at a specific node of the tree, I can throw forward a trial X, but I also generate dual multipliers that I can send backward. The X that I throw forward is a trial solution that will be used in time stage t plus 1 by all of these guys. The notation here is the set of scenarios of period t plus 1 that are born from scenario k. So for example, the descendants of this guy here, yeah, it's t plus 1. So the descendants in time period 2 of scenario 1, this guy, are 1 and 2. The scenarios, the descendants of, in period 3 of scenario 1, so by 1 here, like I told you earlier, I'm numbering scenarios starting from top to bottom. So this guy is numbered 1, this guy is numbered 2, this guy is numbered 1, 2, 3, 4. So what is this? Descendants in period 3 of scenario 1 of the previous time period. Who is born from scenario 1 of period 2?
Scenario 1 and 2.
Right. And in my data set, I give these guys the same name, 1, 2. It might be a bit confusing because these guys have the same name. They're also 1, 2, but they're 1, 2 of period 2, not of period 3. So here, the descendants in period 3 of scenario 1 of period 2 are 1 and 2. The descendants in period 3 of scenario 2 are scenarios 3 and 4. Okay, is the notation clear? Okay, but it's just a way to describe, this data structure is just a way to describe the scenarios in the next period coming from scenario K. So when I solve the NLDS, I can throw a trial solution to the descendants, but I can also send back dual multipliers to the previous time period and the ancestor scenario. A of k is the node from which k is born. So for example, here, A of 1 is 1, A of 2 is 1, A of 1 is 1, A of 2 is 1, A of 3 is 2, and A of 4 is 2. Okay? Okay, so this is the idea. This is the heart of the algorithm, the building block that we will be solving over and over. And any variations of this algorithm just depend on, after we solve this problem, which node we want to move to next. The heart, the style of the algorithm is identical to the L-shaped method. In the L-shaped method, the trick was to ignore everything in the beginning and solve as if there were no second stage cost. We'll do the same here, and we will gradually be building cuts. Okay, so we start from this 3-stage tree. here we solve a linear program which just minimizes, in the first iteration, we should solve a linear program here which just minimizes current period cost, ignoring any future costs. That's what we did also in the L-shape method. We solved that. We will get a bunch of multipliers for this problem, but there's no reason to send them back because we use multipliers for generating cuts, and there is nothing before time period 1 here. So all we do once we solve this optimization is send a trial x to the next time period. Okay. And then we so at each iteration of the algorithm, we have an associated direction. In the code that I will describe to you, there is this piece of data that we define in our code called direction, which indicates, am I moving forward or am I moving backward? When I'm moving forward, I'm throwing x's to the next time period. When I'm moving backwards, I'm throwing cuts to the previous time period. You'll see in detail what this means, but just remember in the code there is one piece of data that indicates the direction that we're moving to. So when we solve here, we generate an x for time period 1, scenario 1. We throw it forward. Then we come to this NLDS here, and we maintain the forward direction. So we solve this guy first. Since we are moving forward, whatever x we get from the solution of this guy, we throw it to the next time period. Then we move to this NLDS here. Whatever x we get, we throw it to the next time period. And finally, we reach the bottom of the tree. And at this point, we change the direction in the algorithm and start moving backward. When the direction of motion is backward, we send multipliers to the previous time stage. Not x's to the forward time stage, but multipliers to the previous time stage that help us build cuts, optimality cuts. This might sound a little abstract, but we'll do an example so you see in detail how it works. So we solve 4 NLDSs here. The dual multipliers of these 2 NLDSs help us build one optimality cut for this node. The dual multipliers of these 2 NLDSs help us build one optimality cut for this node here. And we do the same when we return back to these 2 NLDSs. We get one bunch of multipliers here, one bunch of multipliers here, and we use them to build an optimality cut in time period 1. That's the idea. Now, we'll see this concretely in what follows. I probably, okay. I will show you how the NLDS looks like, and then I'm probably going to jump into the example before returning back to look at the detailed flowchart of the algorithm, because if you don't see a concrete example, it's maybe hard to understand how this functions on an actual problem. So I'll show you some parts of the algorithm, I'll then jump to the example and return to the flowchart of the algorithm. So this is what the NLDS looks like. And it should look pretty familiar to the L-shaped method. Again, we have one NLDS for each time period, and for each scenario. This script k to the power t, this is not a power, it's just indicating the time period. And this indicates the number of scenarios for time period t. So for the tree I showed you earlier, the script k of 1 is 1, the script k of 2 is 2, and the script k of 3 is 4. what are these here? Do they look familiar? There's a way to tell apart optimality cuts from feasibility cuts. Cassandra, you have an idea? Right. So these are the same as the feasibility cuts that we saw in the L-shaped method. These are the optimality cuts. Now, things are almost as they are in the L-shaped method. It's just that there's a slight complication that we're also taking the dual multipliers of cuts we've already generated. If you remember, in the L-shaped method, the only piece of information we used to generate cuts for the previous time period was which multipliers from out of these three constraints. Right, we took the equality multipliers and built this E matrix and the E vector. Here we also keep track of these multipliers here and send them back. Okay, so this is what an NLDS looks like. Again, the cost to go in the future is a piecewise linear function of the current x. So notice here the notation, right? We have a current period cost, which is a function of the decision for scenario k of period t, and a value function for the future, which depends on the current period decision of scenario k period t. So all we're deciding for the current period is xkt. What is this a decision variable in our problem? Is this a decision variable in our problem? It's fixed. It's a trial from previous. So this came to us from t minus 1. These guys, the capital D, little d, capital E, little d, we built them from problems that came to us from period t plus 1. So you see how the data is coming from both directions to an LDS tk, right? The x of ancestor in period t minus 1 came to us from the previous period problem. But the cuts, the multipliers we use for generating these cuts came to us from the future. Okay. And that's basically all I wanted to say about this slide. Okay, now, for like in the L-shaped method, when you are at the last time period, there's no value function to approximate for later. So for the last time period, capital H, for the end of the horizon, we remove the theta, we remove these guys and these guys. It's enough to just solve with this objective function with the linear constraints. Okay, for the first time period, there is nothing coming in from the past, so we just fix this to whatever our data is. Typically, we know for the first period we have a bunch of linear constraints, so we're given a vector. So this just degenerates to a vector b, which is data in our problem, just for the first period. Okay. Now, I'm gonna show you the dual of this problem to show you how we generate feasibility cuts, and then we can go to the example. So, how did I get this? This is the dual of an LTS at time period t scenario k. This is just the standard rules of getting a dual problem from a primal problem in linear programming. Okay. Why are the sigmas 1? So how did I get the sigma is equal to 1? Actually, I may have made a mistake here. I think I've made a mistake here, so I'll try and resolve it with you guys, and hopefully we arrive together to the correct. So I'm going to take a risk for the next 5-10 minutes. Maybe this will blow up in my face, but it's okay. So when we have, well, let's start from the easy stuff. So the max what I want you to be thinking of right now is what happens with the dual multipliers if I get an x from the previous time period that makes the current period NLDS infeasible. And that will give us then indications of how we build a feasibility cut. Okay, so let's think of what happens to the dual problem if the NLDS is infeasible. That's what I want you to be thinking about. So the objective function is just standard duality of linear programming. Okay, I go multiply the pi's with the right-hand side, multiply the rows with the right-hand side, and the sigmas with these. Looking good? Okay. Now, subject to pi k to transpose W2 okay, so here this corresponds to the x primal variable, right? So I go to the original problem, I look where does x show up, I left hit it with a dual multiplier pi. It shows up also here, I left hit d with rho, and also here sigma transpose. Okay, and then it's the rule goes that if x is non-negative, then the dual inequality constraint has to be less than or equal to the coefficients of x in the objective function. You believe this? Now, what primal variable, and I think I have not made actually a mistake. What primal variable does this correspond to? The theta. And where did this come from? We have, whenever the dual multipliers correspond to a greater than or equal constraint in the primal problem, the multipliers in a minimization are non-negative. This also holds true for the sigmas, but trivially, since I already know they're equal to 1. Okay. So this is a dual of the NLDS. How do you, in linear programming, how do you generate a certificate of infeasibility? What does the solver send back to you? When you get an infeasible, well, sorry, let me ask another question. What does the solver send back to you when you get an unbounded solution? But it gives you there's a specific way for the solver to verify that the problem is unbounded. think geometrically. It's two pieces of data, well, two data structures that it's sending. A point and a direction. It sends you a feasible point and a direction that improves your objective function, but always stays within the feasible region. That's a way to verify unboundedness. Does that make sense? So if this is my, if this is my feasible region, can this problem be unbounded? No. But if this is the feasible region, then the solver can verify if the problem is unbounded or not by discovering a single feasible point within this polyhedron and one direction that it can go on forever without violating the inequality constraints that define this polyhedron. And at the same time, this direction has to be improving. So if this is the cost vector, the cost transpose the direction has to be negative. Okay, this is a way to verify unboundedness. So, hopefully we also all remember that if this problem, the dual, is an unbounded problem, then an LDS is infeasible. How can an LDS be infeasible? Well, it depends on what X ancestor from t minus 1 you send me. Okay. Now, what would a direction of unbounded, what would this vector here look like? Forget the point that's within the feasible region. What would this vector of constant improvement have to look like? We've got a bunch of constraints here. So now we're in the dual space because the dual linear program is in the dual space. So we have a certain pi rho sigma, a starting point, and a certain direction pi rho sigma also. Okay. When we plug those in here, the only way to walk down this line and stay within this is what? So think now here that I take any arbitrary starting point pi 0 plus lambda pi, and I'm going to push lambda from 0 to as big as I want. The same for the rho. I start from a rho 0 and I start moving down the direction rho. Maybe the notation, I'll just call it 1. D plus sigma 0 plus lambda sigma 1 E. What has to be true for me to always be less than or equal to C transpose? As far as the pi 1, rho 1, and sigma 1 are concerned. Suppose that pi transpose W plus rho transpose D plus sigma 1 transpose Z were positive. Suppose they were. At some point, as I'm moving down the line, so as I'm increasing lambda, I'll get out of this. Okay, because it's a less than or equal constraint, it has to be the case that the direction down which I'm moving has to be less than or equal to 0. No matter how big, because that way, no matter how big I push the lambda, I always satisfy this inequality. You buy the argument? No? You don't buy it? Okay, you should sell it better. Now, with the same rationale, what has to be the case for the objective function? We're looking for a direction that keeps us always within the polyhedron, but also it improves my cost. So what has to be going on here. With these pi 1s, rho 1s, sigma 1s. The sigma 1, first of all, the first thing to notice, the sigma 1, by the way my dual feasible region is defined, I can't move it. It's fixed, it's slammed at 1, okay? So this basically goes away. So we're left with the pi 1 and the rho 1. So the objective function has to be always improving, which means pi 1 transpose this plus rho 1 transpose d has to be positive. If I can present to you, I don't know how I come up with them, but if I can present to you a pi and a rho that satisfy this, so improvement of objective function, and always staying within the polyhedron of the dual problem, I have just given to you a certificate of unboundedness for the dual problem, which means I've given you a certificate of infeasibility for the primal problem. Okay. Now, when I implement the algorithm, this could very well happen. I might send some x to the current NLDS that results in an unbounded unbounded dual. So I could very well get these vectors, and the way I use them is to build feasibility cuts, basically. So if I get an infeasible NLDS at period t scenario k, are we okay with it so far? If I get pi's and rhos that cause an infeasible NLDS, I build a feasibility cut for the previous time period by creating this capital D matrix and this little d vector. Okay. So the current period multipliers that I get, I don't use them for a current period feasibility cut. I use them for a previous period feasibility cut because it's the previous period decision that made me infeasible right now. Okay. So then I've shown you a recipe of how to build feasibility cuts. So this capital D and this little d, then I create constraints like this for the previous period. And the recipe for building optimality cuts is this formula over here. Now, for the feasibility cuts, I argued in this way. So I'll show you next week in the proof of convergence more formally that they will do the job. For the optimality cuts, they should look familiar, right? And what is different between this and the L-shaped algorithm? There's a couple of things that are different. The formulas are somewhat strikingly different. There's the index by t. We're taking averages again, right, of what happens in t plus 1. But what's new with the formulas? If you remember, again, for the two-stage problem, we were taking an average cut, where the average was taken over the dual multipliers of all the scenarios of the second period. But here we're not doing exactly the same, right? Come again? Sorry. Right. So you look only at the scenarios that descend from a certain node. You don't even care for the other ones. So when I was in this 4-stage tree, do I need the solutions of these guys to build an optimality cut for here? No, I don't use them. Now, if I get pi's and rhos and sigmas from this guy and from this guy, what weight should I assign to them? What weight am I assigning to them? So if the chances of landing in this node are 0.25, exactly. We assign a conditional probability of going here, given that I am here. Not the probability itself, but a conditional given that I'm over here. Okay. So that's a difference from the LCD method. And then the other difference is these terms here now for the little d vector is that the code is keeping a record of not only this multiplier, but also these two multipliers and sending also those back to form the optimality cut. They also contribute to the optimality cut. And we'll see why in the proof of convergence, but for now, if you can believe me, we can proceed. Okay, so that's the recipe for the optimality cut. So I look at all the descendants, I take a conditional probability of going to any of these descendants and build the capital E matrix by this formula here, the little e matrix by this formula here. And once I calculate these vectors, I send them to period t minus 1. Now, 3 scary slides. We'll forget them for the moment, and when we look, hopefully after we see the example, when we look back at the scary slides, they won't look too scary. Okay. This one is not very scary. This is just initializing the algorithm. This one, I tried to make this look not scary, but it doesn't fit. This one is just moving forward, and again, I'll go through this with you in a level of detail that hopefully will not look too bad. But this is just moving forward, and this is moving backward. Okay, and these are all the checks that we need to make to implement our forward-backward protocol. Now, I showed you a specific way to move down the tree. If you notice, well, everyone has to start from the beginning. Any algorithm has to start from the root. But then, I went here first. Did I have to go here? I didn't need to then come to this end. I could have went backwards, you're saying? Could I, well, suppose I come here. Could I have gone backwards with anything useful? Why not? Of here, you mean? You're saying I would need data from here also? There's an even stronger, well, there's another reason why just solving this can't give me enough useful data to return something. Remember, when I'm returning data here, it has to be a cut. Well, okay, if this were infeasible, then yes, I could return data back to generate a feasibility cut. But if this were feasible, can I create an automatic cut? I need also info from the other node. So whenever I want to send some data back, I need to solve all the children of this guy. But once I solve these two, I could, if I wanted to, come back to period 1 and solve it with one optimality cut. But instead I decided to go down the tree. So that's called, and then once I went down the tree, the block diagram I showed you earlier will then, it will scan forward with x's, sending x's forward. then it reaches the bottom, it'll go backwards. It'll go forwards, it'll go backwards. Yeah?
So you're saying we can more or less choose to go backward or forward?
It's up to you if you want, yeah. So one other way to do it would have been to go here, 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 until you reach the end of, it's kind of like branch and bound, right? Branch and bound also decides how to traverse. It's the same idea. So, for example, when you're going, one protocol would be to go all the way forward whenever you can. And that's called a fast forward. Another protocol is if you can go backward whenever you have enough data. That's called a fast back. So there's different ways you can traverse the tree. The way I showed you is scanning all of the nodes first before you make a step forward and the other way around. Let's continue where we left off. So the example has two goals basically. One is to just show you how this thing works. But there's also another important takeaway, which is a difference from how the L-shaped method behaves. So we showed when we were going through the convergence proof of the L-shaped method that the optimality cuts we generate have to be supports of the value function at the specific trial x. Support means an affine function of x that is exactly equal to v of x, to the value function, at the current trial point, and is a global underestimator of v of x. Not so for the nested L-shaped method. The nested L-shaped method produces optimality cuts that can be, that underestimate the value function, so they do describe a lower bound. But it doesn't have to be the case that at the trial x that we are sitting in, the optimality cut is an exact support. It doesn't have to be equal to the value function. So this was a drawing of how the L-shaped method behaved. At xv, we got this optimality cut, and we showed that if I compute this at xv, it has to be exactly equal to the expected cost of the second period at point xv. Again, not so for the multi-cut L-shaped method. I might get a certain x of scenario k period t. I'm going to get a cut. It's a global underestimator. Would the trick, would the NLDS be a relaxation of the problem if this were crossing the value function at x?
No, because we delete feasibility.
We basically, it's not so much that we delete a feasible solution as it is that
It wouldn't be a low.
it's not a lower bound anymore, and we really need that guarantee to make the convergence proof work. So we get indeed a lower bound, but it's not necessarily exactly equal to the value function at the current trial point. And we'll see that happening now. So this is a problem of scheduling how to produce air conditioners. So we need to, we look at a three-stage planning, and we can use regular production facilities to produce the air conditioners, emergency overtime staff, and also store. Classical supply chain problem. So three decision stages. We have a maximum production capacity, regular production capacity of 200 units of air conditioners per month, and the regular cost we pay is $100 per unit. But if we want to use overtime, we can, it's 3 times more expensive, but we can go above the 200 units per month. Okay, we know our demand in the beginning of time, it's 100 units, but then for period 2 and period 3, we have an equally likely demand of 100 units or 300 units. And we can store units at $50 per air conditioner. And there's this constraint that we need to satisfy all the demand. So, the notation. So, X is our regular production, Y is storage, W is overtime, and D is data, it's demand. So this is a little exercise of getting familiar with the notation here. So when I'm at period 3, I'll draw this, although we have it here basically already. Yeah, I don't even need to draw it. When I'm at period 3, for scenarios 1 and 2, the ancestor is 1. When I'm at period 3, for scenarios 3 and 4, the ancestor is 2. And I forgot to tell you who the ancestor is for period 2, but it's okay. I'll fix this in the slides. So, then probabilities. Again, the piece in the data that describes the problem is the chances of landing at this node from the root. It's not conditional. Okay, so the chances of these different nodes correspond to what different input? What's the random input? Demand. So it could be 100 or 300. Equally likely. So the chances of landing in this node are 0.5, chances of landing in this node are 0.5. And again, equally likely 100 or 300 in the third stage. So 100, 300. So then here the weight would be a quarter, a quarter, a quarter, and a quarter. Okay? That's what I have here. And then the notation, again, now you have to familiarize yourself with multi-stage notation. The subscript denotes scenario, the superscript denotes time. So for period 2, scenario 1 is 100 units. Well, he's dividing everything by 100 in the book just to simplify the numbers. Demand for scenario 2 of period 2 is 300, and the vector of demands for third period are 1, 1, 3, 1, 3. Okay, that's the notation you encounter. So this is the full optimization problem that we would like to solve. We have regular production that we pay $100 per unit. So again, we're dividing everything by 100 just to simplify the coefficients. We have overtime production, which is 300 per extra unit. And then we can store in period 1 to send it to the next period, but that costs us $50 per air conditioner. Okay, so that's the cost term here. And note, the storage decision is a first stage decision. So the constraints for the first stage are my regular maximum production is 200 units, and whatever I decide to store in period 1 becomes basically demand for that period, because I have to satisfy the current period demand, which is 100, plus whatever I decide to store. Okay? So what are the sources of my production that I can use to satisfy this demand? I can do regular production or overtime production. Then, looking into the second period, so that's the 2 superscript here. The cost structure is the same. 100 for regular production, 300 for overtime, and $50 for storage. There is no storage cost in the third period. There's nothing to store. Well, you don't even need to add it, right? Because an optimal solution would never bother storing in the last period. So we can just ignore it from the objective And then these constraints here just, again, demand equals supply. So now the supply for period 2 also includes whatever we decided to store from period 1. So this is the variable that creates the link with the past. It's the storage decision. It's what's coming in from the previous NLDS. Okay. And for these are the constraints for period 2 and for period 3. Model is clear. Okay. Now, this is an illustration of how the algorithm behaves. So the block diagram that we saw, the scary-looking block diagram that we saw in a few slides earlier. And DIR will denote direction. Again, remember, when you're implementing the code, there is this data structure that just indicates at the current iteration what is your direction. We start with direction of forward, and we set all the thetas to 0 for all of the NLDSs. Okay, how would the first stage problem look like? Objective function is what does this NLDS at the root look like? Plus? So the first two constraints we're good. Everyone will start like this. Now, when you're coding this, you also have the theta from the start, but then you just add a constraint theta equals 0. If you go back to the block diagram I showed you, which we really quickly ran past, it does this. Because then it's just a convenience of coding. Then you can drop the equality and replace it with cuts. So you can either do this or add the theta and force it to 0. It's the same thing. So that's what the problem looks like the first time around. What is the optimal solution to this problem? I mean, ignore this for a second. So what do we want to avoid is the overtime, obviously. And the only way that we're pushed to use overtime is depending on the demand. There's absolutely no reason we want to keep inventory when we ignore the future. There's no constraints here that give us any benefit for doing it. So I will just satisfy this demand with regular production. I'm at the root, I pass this over, I relay this to the second time period. Okay? So, if you go through all the block diagram I showed you earlier and do all the if, then, no, that dir equals forward or whatever, the protocol sends you to this node over here. Now, the NLDS for this node is the same, basically. It's the current period costs plus the theta, but the theta is forced to 0 because it's the first time we visit that node. And supply equals demand, non-negativity, and the maximum production. Again, the optimal solution here is 1 unit of regular production. But then when we go to the other node over here, can you see the typo in the slide, which I will fix? Yes, demand should be 3, which is why we then use overtime production. Another question is, it seems like I'm not bringing in the ancestor decisions, right? Where did those go? In fact, they were 0. The storage decisions from time period 1 are 0. So they do show up here. It's just that since they are 0, we bring them to the right-hand side and they don't influence the demand for that period. Okay, so the demand should be 3, so I'll fix that. Then we finally go to the last period. Again, the same structure of the problem. Demand is 1. And now we start storing multipliers here. So the pi multiplier is 2-dimensional because we have 2 constraints. So the first entry corresponds to the less than or equal to 2. The second entry corresponds to the equality constraint. And for period 2, over time reduction is 1. This is the dual multiplier. For period 3, it's identical to for scenario 3, it's identical to what it was for scenario 1. And for scenario 4, it's identical to what it was for scenario 2. Now, if you go again through the block diagram, it will discover that it's at the end of the tree in the last scenario. So it now is instructed the program is now instructed to switch direction and start moving backwards. Okay. And once the direction changes and it starts moving backwards, it goes to step 2 of the algorithm, which was the second ugly slide you saw. So step 1 was the first ugly slide you saw, which is moving forward. Step 2 is the second ugly slide. And now we start generating cuts. So when it goes to step 2, it also returns to this NLDS over here. And it creates the first cut for that NLDS. So to refresh your memory, the dual multipliers we're going to use for this NLDS are the dual multiplier of this node, which is I1301, and this node is -2, 3. Okay, so let's go back here. So this is the conditional probability. The formula, again, if you remember, was E, T, K. The second index here is counting how many optimality cuts I have for this NLDS. So we're now at NLDS 2, 1. So time period 2, scenario 1. And the way we compute the first optimality cut is we take the conditional probability of going to time period 3, scenario 1, or time period 3, scenario 2. And we do pi transpose the T matrix. So the 0, 1 here is this. It's from scenario 1 of period 3. The -2, 3 is from scenario 2 of period 3. And the T matrices, do they look reasonable? What does each column correspond to? Well, what does the third column correspond to? Yeah. We had this. Does this affect the T matrix? Remember, the T matrix multiplies previous period decisions. So does this constraint what in our generic notation we have tx plus wy. Now this is confusing because this is a bit confusing with that. Let me see how I can make this better. Well, I'll write it this way and hopefully you won't get confused with the x, which means regular production. So in our problem, we have x less than or equal to 2, x plus w minus y is equal to demand plus, and then on the supply we also have what we got from the previous period. Okay? You remember this? This is just transferring inventory from the previous period. Right? So this is xkt, wkt, ykt. So does this constraint have anything to do with the T matrix? It's a current period decision, right? Okay. So what variable does the third column correspond here to? The y variable of the previous period. And this is how we build the optimality cut for the current NLDS. Okay, this is the recipe, basically. The H vectors, again, this is the x less than or equal to 2 constraint. This is the demand. The demand changes for the second scenario, so we get the right-hand side here. And the optimality cut we get is, we get this capital E vector multiplying xwy plus theta less than greater than or equal to little e. So the 2 entry hits the y variable, and the optimality cut is 2y plus theta greater than or equal to 3. That's the cut we pass now to NLDS of period 2, scenario 1. Okay? So this is how it now looks like. It's the same as before, except for the optimality cut. So now there's, even though our demand is even though our demand is 1, we have an optimality cut that rewards us for producing more than the current period demand. So the optimal solution will be 2. It will also send 1 unit to time stage 3. But it won't use overtime production. It will just use regular production, and the y variable is 1. So it's going to send 1 unit to the next time period. This is the theta, this is the pi multipliers, and the sigma multiplier now corresponds to this optimality cut constraint here. Okay. Still moving backwards, we go to an LDS 2.2. This is the primal optimal solution, the dual multiplier, and the dual multiplier of the cut. We're still moving backwards, so we're scanning backwards. This is how we compute the optimality cut for period 1, scenario 1, right-hand side. This is the cut that's added to an LDS 1.1. So now our new NLDS in period 1, scenario 1, looks like this. So now things have changed, right, compared to when we first solved this problem. And now we have this optimality cut here, and indeed the optimal solution doesn't just greedily produce 1. It produces an extra unit to send it as inventory to the next time period. Now, every time this direction data changes, the convention is we move to a new iteration. So we were already in iteration 2 when we hit the end of the tree and flipped direction. That's a convention I use. So here we're still in iteration 1, where we hit the last node, the last node of the last time period, and the direction becomes back, so the iteration becomes 2. When we hit the beginning of time, the direction becomes forward, we move to iteration 3. That's the convention. So is it kind of clear how this thing is scanning the tree back and forth? Okay. Now let's see what the optimality cut looks like. Let's confirm what I told you earlier, that optimality cuts don't necessarily have to be exact supports of the value function. So what I want to do is kind of like project the optimality cut in a single dimension, which is the total production of period 1, so that you can see it in a two-dimensional graph. That's what's done in the book, basically. So what I'm going to try and do here is drop the y variable, so you can just see this as see the value function as a function of total production for period 1. What is total production in terms of the decision variables of the problem? X plus W. Y is the storage variable. So we have this constraint in period 1 that total production is equal to demand plus inventory that I sent to the future. And we got this optimality cut in iteration 1 when we were moving backward, if you remember. So all I'm doing here is taking this equality constraint, which has to hold for period 1, and substituting the y1 with 1 minus x minus w. Again, that's how I get this expression here. So this is what the optimality cut, again, I'm trying to get rid of the y here, so that you can see the drawing as a function of total production. So I'm doing the same trick of getting rid of the y in the objective function. I'm replacing it by this expression here. So what I'm left over with is z1 is equal to that thing. So let's draw z1 as a function of total production, which is x1 plus w1. What the NLDS looks like is basically this objective function, which I got from this substitution here, subject to the optimality cut, where in the optimality cut I've gotten rid of y. And the lower bound on x is basically coming from the fact that demand is 1. So the first thing you're going to use is regular production. That's why for the optimal solution, using x less than 1 is stupid. So we're just directly enforcing this constraint here. And this is the definition of total production. Now, given this optimality cut, how do you want to what's the best way to satisfy the total production here? You have two options of satisfying it, x or w. What's the marginal impact of increasing x? And think, you would say that just looking at the, but now, yeah, you also want to be thinking now of the optimality cut, right? So if I slightly move x, it's 1.5 from this term, minus 225, right? So how about w? 1.25. So which one hurts? W, we don't like it. So if P were less than or equal to 2, what would I use to satisfy it?
It's 2.
P of
Easy one.
right, exactly. So as long as total production is less than 2, I'm just going to go with X, given this optimality cut over here. Now, if production needs to be above 2, then I have to energize the W. Even though I don't like it, given this optimality cut, I don't have another option. Okay? That's the rationale here. So that's what's going on here. If production is between 1 and 2, I use X to satisfy production and no emergency production. And then if production goes above 2, there's no reason to consider production above 3. Why? It's the data. It comes from the demand data. It doesn't never go above 3. So if production is between 2 and 3, I push X as high as I can, and the rest comes from emergency. Now, if you plug that back into the objective function, you get an expression like this for the cost as a function of total production in the first stage. Then, in iteration 6 of this thing that I didn't have you watch because then you would be sleeping, and eventually we also get an optimality cut like this. So in the book, you're asked to run all the iterations. We did it last year. We implemented this in code, so you can indeed see that in iteration 6, you get an optimality cut like this. And this is the punchline of this whole discussion. What you're seeing in this graph is, in the horizontal axis, total production in period 1. And this blue dotted line is the cut, the first optimality cut we generated. That one we saw together just now. And it's this one over here. And I derived it analytically for you using this whole argument. It's just the blue line is this expression here. Okay? There's this kink at 2, and we get this blue line here. So when we're at this trial decision, we get an optimality cut that is in fact strictly less than the expected cost to go. The expected cost to go is the dark black curve. This cannot happen in the L-shaped method, okay? But it can happen here. Now, if you want to think intuitively of why it can't happen, do you have any guesses? I know it's very premature to ask you something like this, but there's this second order effect of, in the two-stage stochastic program, when we're at stage 2, are we simplifying stage 2? When we solve a stage in a two-stage stochastic program using the L-shaped method, are we making any approximations in stage 2 about the future? Is there a theta variable in stage 2? It's the end of time, right? We are exactly solving that problem for the end of time. So the information we're passing back from the multipliers represents exactly what would happen from stage 2 to the end of time, because it's the end of time. But here, we lose information, right? As we are, in a multi-stage stochastic program, when we reach the end of time, at the last period, we're exactly solving the true problem. But then we are throwing back optimality cuts that are already under approximating the value function for previous periods. So there's this loss of information as you're moving back. That's basically intuitively how I think of why this happens. Only in the end of time are you solving the exact problem for the remaining horizon. So, in fact, in the second cut, I showed you touches on the value function, but the first one doesn't. Okay, that's all about the example. I'll now jump back to this block diagram. We can look at it real quick. And I think that I won't try to get into the convergence proof today because it would take longer than how much time I have. Okay, so let's try and decode these three block diagrams. One sec. Step one is initialization. We start at period 1, scenario 1. This is the counter, I think, for optimality cuts, the counter for feasibility cuts. The counters are set to 0 because we don't have any yet. And we explicitly input this as a constraint to all of the optimization problems, and our direction is moving forward. Now, forward pass. Now we're moving forward. Okay. First thing we do when we're moving forward is we solve the NLDS. After we solve the NLDS, we check if we have a feasible solution or not. Do you remember what the check was? Right. Not the E matrix, the dual multiplier. So we checked two inequalities for the dual multipliers. Right. If it turns out that these multipliers we get satisfy this infeasibility condition, then we're in trouble. We can't go further. So if it's the first time period and we haven't added anything yet, and the first trial decision we get is infeasible for some scenario in the second stage, we stop because we are infeasible. Does this make sense to you? If we're already solving a relaxation of the problem, when we are solving an LTS 1-1, and that's the idea to understand why this algorithm converges and everything. The idea is to always remember we're solving a relaxation. We're solving a relaxation in terms of the feasible region at period t scenario k, and in terms of the objective function. The objective function, we are under-approximating it. The feasible region, we're blowing it up, we're expanding it. If I can't even satisfy the feasible region of period 1, scenario 1, of a relaxation, I certainly can't satisfy it for the full problem. So that's when we exit with the infeasibility. If for period 1 we, okay, if it's not period 1 and we generated a trial X that's infeasible further down the line, then we will just pass a feasibility cut to the previous problem. So if it's not period 1, we will increase the feasibility counter, generate the cut, and here this means these last three blocks, what they're doing is they're saying, okay, you were going down the tree, but you hit a wall because the X you generated, well, if the X you generate here is infeasible for this guy, then you terminate with an infeasible problem. But if the X you generate here is infeasible for this guy, switch directions and send and generate a feasibility cut over here. That's the three last instructions here. So move to period, the previous time period, the ancestor scenario, and change your direction. You were moving forward, but now you'll have to move back because this infeasibility cut will have to propagate back to earlier stages of the tree. Okay, now if there is no infeasibility problem, we proceed. We check the x's and the thetas, we store the dual multipliers. We look at whether or not we are. So what we do is we basically, at each time stage, we scan downwards the scenarios we have. So we're scanning downwards. Are we at the bottom? If we are, then we go back in the top of this procedure and we restart this whole procedure. If we're not at the bottom, so if we're over here, for example, Then we jump to this NLDS here, which means what in terms of changing the K and the T index? The T index, does it change? Remains the same. The K counter increases by 1. That's the idea. So how about this check over here? This check is doing the following. When you first look at this, it seems a bit redundant. So you're checking, am I in the bottom of the current stage or not? If I'm not, I can first ask myself, am I in period 1 or not? What would be the difference if this is something, and I'm not sure I'm going to be able to recover the answer for you right now, but my thought yesterday was, why not ignore these two guys over here and just go straight to the check over here. And this is probably okay. So I will avoid starting to talk to myself for the next 5 minutes, but this was I can't remember which part of the routine this came in handy for, but this is indeed necessary. So if you play around with the code, you can see it happening. I think the idea, well, I'm not going to even get into a debate with myself, but this is indeed necessary. I can't remember exactly for what point of the algorithm you use it, but you do need to go through this intermediate check, otherwise things break. Now, if you're not at the bottom of the tree, you move one. You move one scenario down, oh no, if you're not at the bottom of the tree, you move one scenario down. If you are at the bottom of the tree, you continue forward, but for the next time period. Or, if you are at the end of time, you switch to the backward direction, which is this case here. Okay? So, if I hit the bottom of the tree and I'm over here, then I switch direction, I go backward. But if I hit the bottom of the tree and there's still time moving forward, I maintain the forward direction. And this is the backward step. So here, I'm looking at whether I'm in period 1. The assumption again for step 2 is that you're already moving backward. If it is period 1 and you're moving backward, then you increment, so that means you've just reached the end of a backward scan, you increment the counter and you start moving forward. I suspect maybe I should also have a dir equal forward instruction here, unless that gets taken care of. Actually, that gets taken care of here. Okay, that's why this exists. This is a check of whether we've reached the beginning of time. Okay, coming back to here, as we're moving backward, if it's not period 1 and it's an additional time period, we generate an optimality cut. We do optimality checks. The certificates of optimality were the same as they were with the L-shape method. In the L-shape method, if you remember, what we compared was the theta with the cut evaluated at x. That was our certificate of optimality. So if you remember what we did when we were solving the L-shape method, we had our real value function, and if we had only a single cut, we would come here, supposing, for example, that this is the boundaries of my feasible region. We would evaluate our optimality cut at this level. This we called W. And we compared it to the value function at this level. Sorry, this we called theta. This we called, this we called W. And this theta, so, my God, the other way around. And then if theta was greater than or equal to W, then we would terminate. That basically, what this condition was saying is what I think is the theta is what I think is the value function. Based on all the cuts I have so far, if what I think the value function is exactly equal to the value function, because we get this W for free at the current iteration, then I terminate, because at the point that I care, I have an exact approximation. But if this is not true, then I need to continue. So at this stage, this would not hold true. Then we would generate a cut like this. We would come over here. This would become the new theta, the new W. Theta greater than or equal to W. No, there's still a gap. So then we would generate a cut over here, and here indeed theta is greater than or equal to W, and we would terminate. It's exactly the same thing is going on over here. Okay, I think that the best way to see this is probably also to experiment with the code. So what I would like to do is probably stop here for today, because if we don't stop here, I'll have to get into the convergence proof, and that's not a good idea right now. But I have asked Matthew if it's possible for him to add some exercises where you can play around with an LDS code that we used last year. Now, as far as practical things are concerned, this is a more complicated code than what you need for SDDP, which is the target algorithm for the project. So it helps you if you toy around with the NLDS code to understand SDDP, but it's going to get simpler with SDDP, not more complicated. So we'll see how we'll handle this in terms of exercises. Now, as far as, for example, exams are concerned, obviously you don't need to remember a graph like this. There is no amazingly deep thing about this graph. It's just a protocol of moving back and forth, so no reason to really be concerned. What I really want you to remember as a takeaway from the class is that we're just exploiting the L-shaped algorithm idea, and keep in mind, that the fact that there are differences, there are departures from the L-shaped algorithm. Why the optimality cuts that we use are the proper ones, why the feasibility cuts are the right ones, those are the things, that's the real important stuff about this algorithm. Okay, so with that, I'll see you in a week, and I'll probably steal one of Matthew's hours for the training section next week.